We are changing gears. So we went from looking at really big things in space, and we're going to go to really small things. Um, so, static electricity, there are definitely some connections with your knowledge of chemistry. Um, so, do a quick little chemistry review. So, before we do that, by the end of this lesson, you'll be able to describe what happens at the atomic level to conductors and insulators when next to a charged object, and describe different ways to attain an electric charge. So, quick chemistry review. We find protons and neutrons in the nucleus whirling around the outside. We find electrons. Protons are positively charged, electrons are negatively charged, neutrons are neutrally charged. In this class, we don't care about neutrons. They just add mass. Not very interesting. Okay. Electrons and protons are where it's at. Okay. When there's chemical bonds going on, which of these three are the ones that are like the main focus to understand how things bond? Electrons, right? You're trying to go for your 8, make it happy. Okay. Electrons are where that's our focus. It'll continue to be our focus in this class. Okay. So an object will have a positive charge when what? What would cause it to have a positive charge? It's positively charged because it has more protons than electrons. And it's negatively charged when? More electrons than protons. It would be neutrally charged or no charge if equal number. Balanced out. Okay, good with that. If objects that have the same charge are brought near each other, what will they do to each other? They will repel. And if they are oppositely charged, they will attract. Okay, good with that. Okay. This may or may not have been explicitly stated in chemistry, but it's a thing. And you played around with this idea of conservation of charge. When chemical reactions go on, or physical changes or whatever, those chemical reactions do not destroy or eat or birth or create electrons or protons. They're always there. They're just rearranged in different ways. They're okay with that. You're just mixing, you're shuffling them in a different order or different arrangement, but they're all there. At the end of the day, they're still there. You didn't create any, you didn't destroy any. Okay. So that's still a thing in this class. They're always there. They're just in different arrangements. Okay. If there is one fact that I want you to walk away from, if you remember nothing else, this is the most important fact. Electrons are the only thing that move. Okay. Protons are stuck in the nucleus. Electrons move. Okay. Good with that? Electrons are the only thing that transfers. Okay. Talking about conductors versus insulators. Give me some examples of different materials that are good electric conductors. Conductors of electricity. What is that? Copper. I'm going to say salt water. And silver. metals. Okay, I'm okay with you just putting metals. 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 MET. Not like got the bronze. Fourth place. You're not a conductor. What? Bronze is so.
Gold, silver, bronze.
Yes.
Yeah. Oh, so
yeah.
yeah.
Yeah, that's a good conductor. All right. So metals. What do they do? Why is it a good conductor? Because they transfer electrons easily. Conductors transfer electrons easily. Okay. Microscopically, why that happens. In chemistry, here's your periodic table. Metals happen down here, transition metals in the valley. Okay. And I don't know if your chemistry teacher ever said this phrase, but this is a popular characteristic because they have a sea of electrons. Okay. Which means this. When you get a whole bunch of metal molecules together, they collectively share their electrons. It's like, hey, man, my electron's your electron. That's cool. Yeah, that's cool. As long as the total number of electrons works so that they all have 8 or whatever, they're happy. They don't really care where they're arranged. They're just, or where they're located, just so long as we've got them somewhere in the mix, we're good. Kind of reminds me of a hippie community. Like, dude, my electron's your electron, dude. Hey, can I go over to Billy's house? Yeah, man, you can go over to Billy. Okay, cool. And just kind of like, it's a collective. Good with that? They share. Okay. Comparing that to an insulator, give me some examples of materials that are good electric insulators. Fun. Rubber. Plastic.
I was gonna say plastic.
There's lots of them.
Foam.
Foam.
Boom.
Fiberglass. Wood. Ceramics. A lot of different options. Okay. Insulators don't. Not always. Not insulators don't transfer electrons readily. Okay. They don't transfer electrons readily. Their electrons can still transfer. It just doesn't happen readily, easily. Okay. Microscopically, here's why. So insulators have more of a covalent bonds, and they are. Remember in chemistry when you're doing your Lewis dot structure and you're counting 8 electrons, okay? And like, so insulators are more possessive of their 8 electrons. Like, I got my 8. Like, hey, can I borrow one of your? No, I got my 8. Get away. Like, hey, do you mind watching? No, I've got my 8. Stay away. Kind of reminds me of American Suburbia. Okay. Hey, could I borrow your lawnmower? No, go get your own lawnmower. Like, what do you? I got mine. I don't want you to ruin it. Like, you just no. Like, buy your own. Like, hey, can I go over to Billy's house? No, you're grounded for life. It's like, okay, it's just everybody's in their little picket fences. No one really cares about what the other person's doing as long as you're self-sufficient and life goes on. Just don't disturb me. I won't disturb you. Life goes on. Sounds like a wonderful place to grow up, doesn't it? Okay. All right. So if you look up, I guess here's a big distinction between how we're going to learn this in physics versus how you learn it in chemistry. In chemistry, you focused on a single atom or a single molecule. Like when you're drawing your Lewis dot structures, it was of a single molecule. In physics, we care more about an object, a macro-sized object that you can like see, that you can hold, that you can like feel like, yep, okay, which has a ton, trillions of atoms and molecules. And they form together to make some kind of crystal lattice. This is like a crystal lattice for salt. This is my model of a crystal lattice. Let me just explain it to you. Positive is where the protons are in the nucleus. This does not just mean one proton. This just means the nucleus where the protons are. Electrons are on the outside. This does not mean there's only 4 electrons for every 1 proton. This just means you got electrons on the outside. We're going to say that this material, this block of something that you can hold in your hand, is neutrally charged. Okay, so you got a neutrally charged object bar of something. Okay, good with that? Now, what we're going to do is we're going to bring our a negatively charged object near our neutral bar slab of stuff, and we're going to say this is going to be a conductor. Okay, this is not an electron. This is like a negatively charged bowling ball. And we're going to bring our negatively charged bowling ball near a neutral slab of metal. What do you think happens microscopically when we bring this negatively charged object near this neutral metal, piece of metal? Here are your options. Do the protons move towards and electrons move away? Do protons stay put and electrons move away? Do electrons go towards and protons move away? Do electrons move towards and protons stay put? Everybody have a guess? Thumbs up if you have a guess. Hopefully you've eliminated choices C and D because opposites attract and likes repel. Good at that. Okay. Correct answer is B. The reason why B is better choice than A is because protons are stuck in the nucleus. The nucleus does not move. The crystal lattice does not shift. It's just the electrons that are free to move in our sea of electrons. Okay, so electrons run to the far side of the metal slab, like repelled by this. There we go with that. But protons stay fixed in the nucleus. Okay. This arrangement we give a term for, like we have a term for this type of arrangement. Okay. We say that this metal slab has been polarized. Okay. You might have heard polar before, not polar bear, but like in chemistry, like water, H2O, is a polar molecule, right? Like one side was partially positive, the other side was partially negative, but overall, it's a neutral molecule. Good with that? Okay. Here, Did we lose or add any electrons? This metal slab is still neutral, but one side favors a charge. It's more, the electrons are more concentrated in one spot than another. So this side is partially negative. This side is partially positive. It's polarized. You all right with that? Okay, so when I say something's polarized, that means the charges have segregated, have been moved. Okay, good with that? Okay, we just talked about that. So that was an insulator. No. This was a conductor. What happens if we do the same experiment but with an insulator? How does that respond in an insulator? Here are your options. A, no response, just like whatever. B, the electrons run to the far side of the molecule, and that happens throughout the entire slab or block of plastic. Choice C, the electrons run to the far side of the slab of plastic. D, they run to the far side of the molecule, but that only happens near the negatively charged object. As you go on the other side of the slab of plastic, these molecules are not affected. It's more of a localized response. Thumbs up when you have a guess. Correct answer is D. This is what a conductor does. Okay. The electrons are trapped to their nucleus. Okay. So in the suburbia analogy, these guys are like plastered on the backside of the fence, like no, let me out. Like, no, you can't leave. Okay. Being repelled by this thing. But as you move away from this further, that effect diminishes. So over here, they're like, what? Like, that stinks to be you. Good thing I'm not affected. Okay, get to that. Okay, this is a difference between chemistry and physics. Chemistry, you'd say C, it won't do anything. It's neutral. It's like Switzerland. You bring a proton next to an or an electron next to a neutron, is like whatever. But in physics, because we're looking at a macro-sized object can polarize and therefore can attract. Okay, here's an example of that. If you take a balloon and you rub it on anybody else's head but mine, it'll stick to a wall. Okay, you're charging the balloon, and you bring it over this neutral wall, and as you do that, the electrons in the molecules are repelled to the far side of the molecule. And so the molecules themselves have been polarized. The fact that the positive is closer to the negative means that there's a greater force of attraction than there is repulsion between these things. so the balloon sticks to the wall. Good with that? So a charged object can stick to or be attracted to a neutral object. Talk to your neighbor.
Oh wait, yeah.
Because there's no way that we have to read the discussion.
I know you should.
I think the best book I've read.
Okay, correct answer is F. There we go with that. Okay, can it attract neutral objects? Static cling. It's a real thing. Okay. Now, there are 3 different ways where an object can become charged. The first way, charging by friction, is something that you're probably most familiar with. If something becomes statically charged, electrically charged, it's probably this way. Okay. So this happens when 2 different materials are rubbed together and it rips electrons off of both materials. Okay. So we've got these displaced electrons who don't have a home. If one of this material likes electrons more than the other one, then electrons will go to the one that likes electrons, and that becomes negatively charged. The other one will be lacking electrons, electron deficient, so it'll be positively charged. Okay. This occurs, evidence of this will be if you ever get shocked by something. So think of times where you've been shocked, not like sticking your fork in an outlet, that type of shock. I'm just talking about like, oh, you shocked me. Think of those times. What enabled that to happen? Like, what are those scenarios? Give me some examples of when you've been shocked.
Going down the slide.
Going down a slide. Guess what's rubbing? Your pants against the plastic slide. Other examples when you've been shocked. Yep, but before you touch the doorknob, what do you think was rubbing? Socks on the carpet. CJ, do you have a? Yep. Pulling a blanket off the couch, taking a coat off, jumping on a trampoline, petting a cat, getting out of a car. All those are examples of like dribbling a basketball. All those. Okay. So So this type of charging scientifically is known as triboelectric charging. So when two materials are rubbed together, electrons are always being ripped off. But which material they would rather be on has to do with, I don't know if you've heard these phrases in chemistry class, but electronegativity or electron affinity. These are some of the characteristics that govern which material likes electrons and which ones are okay with losing them. Okay, so these materials here are okay with letting go. Tends to, not always, tends to be more organic materials. Those materials that would rather have electrons have a tendency to be more man-made. It's not an always thing. Okay, so up here you get like your wool and your fur, human body or hair, cotton. Down here you tend to get like your polyester, your urethane, polyethylene, vinyl. So like your saran wraps or your styrofoam, like styrofoam cups or PVC pipes. If you ever cut PVC pipe, the filings are like all staticky, like saran wrap. That's why. Okay. So if you take wool and you rub it with like polyester, sparks fly. Cool with that? So that's charging by friction. Okay. So let's say we charge a sphere of metal by friction, make it negatively charged. How will the electrons arrange themselves on this ball of metal? Will the electrons disperse throughout the entire volume of the sphere? Will it go through the entire volume but be more concentrated where you rubbed it? Will the electrons only be on the outer surface but equally spread out? Will they be only on the outer surface but more concentrated where you rubbed it? Or will it just be where you rubbed it? So one of the beauties with this semester is that I don't have to fight against your preconceived understanding of physics. Like last semester, like I think the ball should do this because when I did it when I was in second grade, it did that. Like there's no prior experiences that you can draw bad conclusions from. Here, I'm just going to tell you, and you're like, okay, okay. Factoid. Correct answer is C. On a conductor, the charge always resides on the outside, always. Not in the middle, but on the outside. Okay? And it evenly distributes itself. Good with that? Okay, but what about an insulator? If we charge an insulator by friction, correct answer is E. It's going to be charged only where it was rubbed. Does that make sense with the whole suburbia analogy? Okay. All right. Second way is charging by conduction. So one way to remember this, conduction, think contact, touching. Okay. This happens when a neutral object touches a charged object. Allowing electrons to transfer. When a neutral object touches a charged object, allowing electrons to transfer. The most important word there is touches. When two things touch, that allows a bridge for electrons to transfer. A bridge, a road, path. Okay? Charging by conduction. Good with that? Okay. So here is an example. So we have our neutral piece of metal. We bring a negatively charged object, not an electron, but like a bowling ball. Okay. Near it. Electrons polarize, run to the far side. Now, if we take this negatively charged object and we bring it to the point of touching, this allows electrons to transfer. If you're an electron in this negatively charged bowling ball, where would you rather be? Bowling ball or on the metal slab? The slab is looking way more inviting. It's like, dude, so many electrons. And like, oh yeah, man. Woo, yeah. Hey, how you doing? Hey, this is way more spacious over here. I like this. This is a good upgrade. Good with that. And we just made that once neutral piece of metal what is now charged? Negatively charged. Okay, charging by conduction. Conduction can also happen if you hear a spark or a shock. Anytime you hear a shock, that's electrons transferring. Okay. Give this one a shot. Have a conversation. Okay, what do you say? Correct answer is C. So when we bring this to the point of touching, the electrons in our neutral metal are like, whoa, look at all the protons. And so when you touch that, they jump ship. Let's do that in black. Electrons jump over here, making this electron deficient, making that positively charged. Good with that? Okay. Charging by conduction. All right. Before we talk about the third way, we need a little bit background information. Have you ever heard the word electrically being grounded or connecting to ground? Something like that in terms of electricity. Ground is anything huge and neutral. Okay. When we talk about wiring in your house, the ground wire, which is the bare copper wire, is literally connected to pipes, like water pipes, and then which is therefore connected literally into the dirt, goes to ground. That's where the phrase comes from. Okay. The earth is huge and neutral. Okay. And it has this idea of if you took a 5-gallon bucket of water and you dumped it into the ocean, did you raise the sea level? Well, technically, no, you really didn't touch it. Okay. So even if we put like 5 zillion electrons into the earth, it's still neutral. Does that make sense? Okay. The frame of your car is considered ground when you're wiring up like circuits on your car. Tomorrow in lab, you are going to be considered ground because you're going to be huge and neutral compared to the objects that we're going to be interacting with. Okay. So, some examples, like if you ever work with some circuit boards and stuff, sometimes they'll connect a grounding strip to your wrist so you don't accidentally shock the circuit. Other times, other examples is when you're unloading a semi, you get some charging by friction. It would really stink for like a gasoline truck to like have a shock go off, and so they have this grounding wire to prevent that. Also, like at grain elevators, the corn or soybeans rushing by create a lot of static buildup, and if the shock goes off and the dust of it, that can combust. It's a bad idea. So you have a ground wire. Okay, this is something that's like super low risk, but it's super easy to prevent. So I do it all the time. When you go to fill up your car with gasoline, there's a slight chance that you've built up a charge getting out of your car. And so as you go to fill up the gasoline, there's a chance, small chance, that when you like put the nozzle in the car, you're connected to all that, and there's a shock that goes off that could be ignited, could be small chance by the fumes. So super low probability, but I always just touch my metal frame of the car before and make the shock happen between my hand and the car versus the nozzle and the car. Easy. That's good. Okay. All right. So, the third way is charging by induction. Okay. Um, this is an involved process. So I'm not going to write anything until after I go through the example. but multiple steps. Step one is we have our neutral conductor, and we bring a positively charged, positively charged object near. Visualize what happens inside the conductor because of that positively charged object. So electrons in here are like, ooh, look at the positive, and polarizes. Good with that. Step two, we connect the opposite side to ground. Schematic diagrams or like electric circuit diagrams will have this symbol. That means you're supposed to ground it there, like connect it to ground at that location. Don't worry about that. I'm just trying to make connections with if you've been exposed to that. Okay. So we're connecting this, we're grounding the opposite side. So what does that mean? We're connecting it to earth or ground that has an infinite sea of protons and electrons. So 1-to-1 ratio. The killer is electrons are always looking for a better ratio. They're not satisfied with a 1-to-1. They're like, dude, they're greedy, selfish. Okay? So if you're an electron, where would you rather be? In the ground, we have a 1-to-1 ratio, or here, where it looks like you got a whole bunch of exposed protons. Electrons are like, hey, hey, how you doing? And they come up here. Like, wow, look at all this space. Woo, living large. Yeah, okay. Does that make sense? How that's working? And then we remove the ground. So we take away their path to transfer. Anybody seeing the stage that's being set right now? And then we take away the positive, and the drama starts. These guys are like, man, I guess I'll go back home. They come back like, what? Who invited you? What? And this now is charged how? Negatively charged by the process of induction. Okay, so induction process of charging by induction. A charged object is brought near a neutral object causing neutral object to polarize. A charged object brought near a neutral object causing a neutral object to polarize. Then the opposite side of the object is connected to ground, allowing electrons to transfer. Whew. Mouthful right there. Charged object is brought near a neutral object, causing the neutral object to polarize. Then the opposite side of the object is connected to ground, allowing electrons to transfer. Give that a shot. Thumbs up when you have a guess. Have a conversation.
Just didn't do it.
I don't know. Yeah, it's like, no. So weird. A group and they didn't send anything and I got to listen to my teacher.
Correct answer is? All right, so we have a negatively charged object. Electrons run to the far side, polarize. Then we connect this to ground. So our electron's going to want to leave here or come up from here. Leave. They're like, I'm out of here. I don't need no. So electrons leave. And then we remove ground, making this electron deficient. So it is now positively charged. C. Good with that? We got a pre-quiz due tomorrow by 7:30. Okay. We got a lab tomorrow.